All right, so before we pick up where we left off last time, I wanted to quickly go over the final project, which we haven't talked about yet. But we'll do that today. So this class came about because when I was in grad school, I was taking all these like stats and regression classes, and it's kind of interesting to learn about all the theoretical aspects of it, but the application of this to your research is really kind of what we're trying to support here. And so really you should try and be thinking about how the skill sets that you're learning in this class can apply to potentially projects that you're working on in the future. And actually a lot of students who've taken this class, a lot of their projects have sort of translated into actual like graduate research, or sometimes they're bringing in their own graduate research, but yeah. And so really we want to make this kind of as helpful as possible for you. And so keep that in mind when you're thinking about what sort of project that you want to do. Okay, so some quick overview. So this, I think I had already shown some of these dates. There are all this information is available on Canvas. So project proposal is due on May 5th, and then the presentations are going to be essentially 1 month from then, on June 5th. That's going to be happening during the last week of classes, and so we'll have presentations on the 5th and on the 7th, and then the next week, which is finals week, you'll have time to work on the project report, which is due at the end of finals week. So these are the dates. And there's a rubric for all of this available on Canvas. If you've taken my other class, this is like very similar, right? Things to think about for your project proposal. And I should actually also mention, since I don't think it's actually in any of these slides, so the projects can be group projects, so you can do 2 or 3 people, 3 at the most. Okay? So what data will you be using for the project? This is probably one of the largest hurdles and one of the things that you want to get out of the way. I don't want to say out of the way, but you want to try and do this sort of as early as possible. What data are you going to be using for the project? And in the proposal, by providing this overview, it's giving me some perspective about how much work you've already put into at least identifying the data that you want to play around with in the project. So size of the data set, what's the source, and then when I say summary table of data, that really means giving like a high-level overview of basically what's contained within the data. And then hypotheses that you want to test. And I should say, as far as all of this goes, it's a proposal, so things can change, which is totally fine. That happens actually fairly regularly. But we do want to make sure folks are on track to at least start thinking about this for the final project. Okay, any questions about any of this? Okay. So the final project presentation, it'll be like a 10 to 15 minute presentation. What did you learn from the data? Interesting overview of the data, and then analytical results. And lastly, project report. Really kind of walking through the process that you took to conduct the analysis, stepping through what sort of hurdles that you might have had, what techniques that you were employing and why, right? All of this should be present in the report, not as just a way of me saying, okay, this is what you did, ABC, but also like going through that process yeah, we'll make it hopefully as productive as possible for you, because I will try and provide feedback if that's something that folks are interested in. Okay, yes.
Would we also provide our markdown file supporting the
Yes.
analysis we did?
Definitely, yeah. So in a similar manner to the homeworks, we just want to make sure that the stuff here is replicable. If you happen to be working with some crazy data set, we can talk about it separately. Yes.
Will we be required to use certain techniques in court? So like, no matter what, you always have to have, I'm making something up, an F statistic. You have to like interpret that. Like we don't have to have like, we must have some interpretation of a different statistic that we pull out, right?
Well, what you're expected is that for any kind of question that you're trying to answer, that you're using the appropriate tools and methods and techniques, right? Because what you're talking about is exactly what I'm trying to not do, right? Which is to prescribe, you must do this type of regression and give me this like statistic, blah, blah, blah. It should be appropriate to your analysis. Okay, great. So let's jump back around one moment. So as I mentioned in the video, for those who watched, we're going to kind of continue where we left off with that particular example, regression example with the wages. So let me go ahead and load in that data. So we're going to use the same wages file as we did last time. And just as a quick refresher, why don't we do this? You can look at the structure of the data, right? We've got 6 variables here. Earnings, or annual earnings, which is our response variable. And then we have height, gender, race, education, and age as our explanatory variables for the earnings. Okay. So what I would like to do now, okay, did anyone have any questions from last time? Was there anything confusing that you guys are dying to ask about? Yes.
For the leverage method to identify an outlier,
Okay.
to apply that to a multiple regression model, if we want to know that if a particular regressor, let's say x2 or x3, is associated with some outlier that's showing up on that leverage plot, do we simply change the x in the leverage plot to the x2 or x3, or whichever regressor we want to look at?
Leverage is not a function of your individual regressor. It is the particular data point, right? And so, all right, we're trying out this new system. Hang on. Okay, so if I had a table y, x1, x2, x3, right? And, you know, I have my values like this. The leverage is not in reference to the leverage of a particular variable. It is in reference to a particular point.
It's a particular y value that's
No. So there is a, let's say this is 0, 1, 2, 3, and then whatever these are. 8, 9, 10, 11. Okay, so leverage identifies like this point as a high leverage point. It is not referring to a regressor as a very as something that a regressor in itself does not have a lot of leverage. It's a specific point.
so in the leverage plot where we tried to see the x-axis values and then the associated leverage with it, why did we plot that then?
Oh, it's just like an index value basically. It's
like
just
a position of that particular
yeah.
value.
Yeah. In a multivariate one, you would just do it by the index. So in this table, if I had an index I, 1, 2, 3, 4, 5, indicating the first point, second point, third point, you would just plot leverage against your i's or something like that.
Okay.
Yeah. Make sense? Okay, great. Any other questions about outliers or anything like that? Okay. Let's jump back to this, and we'll do a little bit of review here as well for the wages. I kind of walked through a bit of the like diagnostics on you know, specific issues with the model that I was showing last time, but we'll kind of put that aside for today and just focus on interpretation. Okay, so we're going to start with our simplest model here, and this is going to be actually, I take that back. We're going to start thinking about our categorical variables first, because I want to spend a little bit more time there. This tends to be one of the like trickier areas for interpretation for folks who haven't who haven't worked in this sort of area before. So I want to make sure that we all get a decent sense of what we're looking at here. So I'm going to run basically one sort of simple example. Okay. So who can tell me what races are represented in our data? So don't worry about the results or anything right now, but what are the, how many and what races are in our wages data? Yeah.
It appears there are 3 Hispanic or other.
No. There are 4. So you're looking at the results, but look at the data really quick. Yes.
One of them would be the base with which these are compared.
Forget this. Just the data. Yes.
White, black, Hispanic, other.
Great. White, black, Hispanic, and other. So those are the 4 races. It's not here. You have to actually look in the data. So you can see that here. Or we can query it. We can say, right, unique wages dollar race, and you see those 4. And so that's, one of the common areas of confusion, right? So why is it that when I run the model, there's only 3 of them that show up? Yeah.
Because it's considering the misfactor factors, so like taking the ratio of Hispanic to Black, ratio of other Black.
So close. It is setting one of the races as a baseline value. So in actuality, you can actually think of these as essentially 4 different intercepts. So what this means, if I were just to interpret, so the race that gets left out is the one that is being acted as the base value, which is our intercept, okay? And so, what did I say they were? Black, okay, so black is the one that's left out. So the way that I would interpret this is that on average, in our data set, the annual average earnings of someone who is black is $28,372 a year. Okay? So hopefully that piece of it is straightforward. Before I go into the next set of interpretations, the reason why it was chosen as the base level is just alphabetical, okay? B, H, O, W. I can choose to have a different, race be my base level if I wanted to, and the way that I would do that would be something like this. I would just use a function called relevel, because these are factors. They have levels that set the order in which they are, and the default order is just alphabetical. And if I wanted to change that, I can do something like this, where I would change the reference level to another race. And so if I did this, it doesn't work for
So
some.
they're not set as factors.
Oh, real? Oh, yes. It is because, of course, this is old code, or I'm drawing from old code. Fread is from data tables. Data tables doesn't draw things in as factors. So I would have to set it as a factor first. So let's just go ahead and do that. Good catch. Factor wages dollar raise. And in fact, the way that the levels are set by default is alphabetical, as I was saying. So that would look something like this. And then if I wanted to change it, I would do this. Okay, and so if I run this regression again, now you'll see that this number changes. And now it's at 33,000, and the rest of these are negative. So what's going on with the rest of these? Who could help me interpret this number here? Yes.
Compared to a white person, a black person has 4,993.
Yes. Exactly. And so when we talk about base level, that is the reference in which all of the other categorical variables are being compared to. Okay? And in fact, I can do something like this. 3365.4 minus 4993.3. Okay. Oh, no. What did I do? I missed another 3. Okay. So if I did basically exactly as you were saying, 33,365 minus 4,993, that number is 28,372, which is this number right here, 28,372. Okay? And so if I wanted to calculate how much a Hispanic person would make in this data set on average for annual earnings compared to a black person, it would be 28,372 minus 2,887. Okay? So that would be like 25,500, something like that. And if you do the same calculation here of this minus that, you'll get the same number. Okay, so everything is kind of in a different sort of reference level to each other. Okay. Yes.
So that explains why the p-values are so different, because
Okay, yes. So with the p-values, so forget about the other three for a second. The p-value for my intercept refers to whether or not I think this intercept is statistically different from 0. Yeah. So that one should be clear to everybody. So these values are saying whether the differences are statistically different from 0, which means that how statistically different is each of these races' earnings from my baseline, so in this case from white, right? Hang on one quick second. So this is saying that on average, someone from other race makes $1,000 less than someone who is white, but it's not statistically significant, and therefore our conclusion is that people who are from other races basically do not earn statistically significant different amounts from people who are white. Okay? Yeah.
Can you only compare one race at once with the baseline, or can you do a multiple? So I wanted to compare if the intercept or the white race compared to black, Hispanic at the same time, like together, as like make a claim that black and Hispanic races earn this much less or that much less, more than or less than the white race. Like essentially, while putting both sort of factor variables, black and Hispanic, to one and having a combined effect, can you do that? Would that interpretation be valid?
You could do that. You could like just create a different column where instead of 4 races you would have 3 races, and you could just combine
These
black
two.
and Hispanic. That would be a
And that would be one only when these two appear together, essentially. That dummy variable value would only be one.
yes.
Okay.
Yeah. Okay, so when I think about this, essentially the way this works is, how do I make a new screen here? Okay, there. Essentially, you've got your so this might be white, and then you have lines for each of the races. So this would be other, Hispanic, black. And so if white is your baseline, right, so then that's the intercept value. And then each of these would be intercept plus other coefficients, intercept plus Hispanic coefficients, and our intercept for black coefficient. And any measure of statistical significance for the non-baseline ones is just indicating how different statistically any of these lines might be from a baseline. All right. Questions? Yeah.
Can you just overview the significance and how you interpret?
Yep. Let's do that. Let's hop back to here to do that. So right here, I'm saying someone who is white makes on average $33,000, and we believe that that is highly statistically significant. In other words, it's unlikely that they would be making, it is highly, highly, highly unlikely that they would be making $0 or less, okay? And for someone who is black, they make on average $5,000 less than someone who's white. And there is statistical significance at the 10% level to indicate that people who are black make a statistically different amount of money than someone who is white.
So
Right.
that's not significant.
Yeah.
The difference is not.
Yeah. So the difference. So we think that the difference is greater than 0, more than like 91% of the time.
Yeah, and you use like one standard deviation or two standard
Yeah.
deviations.
Yeah. So it's 1.7 standard errors away from 0. 36 standard errors, 1.7 standard errors, 2.1 standard errors. Okay, great.
One question.
Yes.
How do you interpret the F statistic here in its p-value?
Yeah, so the F stat is down here. So this is determined by that equation that I gave. And essentially what this is saying is that the hypothesis that all of the betas are equal to 0, we reject because at this p-value, we would reject at the 10%
10%
level
level.
because this p-value indicates that it's pretty unlikely.
That everyone makes 0
Uh,
as an amount, or
yeah, that these
All
these would all happen to be 0.
okay.
Yeah. Yes.
So the adjusted R squared and R squared are really low. So that's because we're just using the races against each other and not trying to use the other variables to explain variation.
Yeah. So you can imagine that, like, hey, do all white people make $33,000? Probably not, right? So there's probably still a good bit of variation that happens within each of these buckets.
So does that make this kind of comparison invalid outside of just a teaching tool?
No,
Because
not.
it explains so little of the variation.
No, I don't think so. And that's because you can have something like this. Let's suppose I have this graph like this. And I have points that look something like this. So in something that's spread out like this, where you separated the reds and blues by a categorical variable of some kind, maybe this is indicating a line here and a line here. If you think about how much of the like spread that any individual line is capturing, it's not that much, right? Like points are still like all over the place, but I'm still able to identify, you know, something specific about the data that the model can like tease out, even from like something fairly simple. And so something like this would have a very low R squared, because the amount of variation being captured by these fits is not very good. But that doesn't invalidate the fact that, right, that there's probably something different about blue and red. Yeah.
And this difference is on average, essentially.
Mm-hmm. Yeah. And again, you know, that's why we say don't just look at the R squareds. Hopefully I'll pound that in by the end of the class. Okay. So now let's move on to leveraging this for some simple examples. We're going to do earnings compared to sex. Then we'll do earnings compared to education. And we'll look at both of them. And let's just interpret these guys one at a time. Okay, so regressing earnings on sex, regressing earnings on education. Oh, I already ran those. Okay, running earnings on education and sex. So who wants to help me out here? What is this telling us? Yeah, just help me interpret these coefficients.
There is a large difference between the male and female intercept.
Yeah. But even more simply, what does the 24,000 refer to?
Oh, that the earnings for that particular baseline.
Okay.
characteristic.
And the baseline is female, exactly, right? So we have sex male and sex female. Female's left out just because F comes before M. So that means on average in our data set, females make $24,000. And that is statistically significantly different from 0. And on average, if you are a male, you're making, what is this 21,720?
21,000 more or something.
Exactly, yeah. So this means the average wage for a male in this data set would be $46,000 essentially. And notice that in this case, this is also statistically significant, which means that it's highly unlikely that male would be making the same as a female. In other words, that this is different from, statistically different from 0. I don't know how old this data set is, but it is real data, so. Okay, let's look at the second model, which is regressing earnings on education. Great. All right, who can help me out here? Interpretation. Anybody? I'm sure I've volunteered someone. Yes.
I think it means that with every unit increase in how many years of education you have,
Yep.
your earnings increase by 4490.
Yes. So you're making about $4,490 more on average for every additional year of education that you have. Our intercept just means it assumes zero, right? So technically, if you had 0 years of education, you would be making negative $27,000. Although, right, that's not really a thing in our data set. It's extrapolating. You know.
In our data set, the minimum of the education goes to 3. So is it taking 3 or 0?
No, it would be 0. Switching back and forth is a little more cumbersome in this one. Okay, so essentially what's happening is if I have something like age versus earnings, or sorry, not age, education. Where's the eraser on this one? There we go. So education, that would look something like this. Oh my gosh. Nope, hang on, sorry. It's probably this one. Okay. Maybe you have something that looks like this, and then you were saying there's an education at age 3 or something. Maybe you have like a data point like that down there. Might be some kind of outlier. Although in this case, hypothetically, if I drew my points better, it's just saying that it's negative, right? So it might go down here. So that's why you would have a negative intercept. That's all. Okay. Great. So now we have a nice sort of interpretation of our education, and hopefully this one is a little bit more straightforward to you guys, right? This is kind of what we've been operating on previous to our dummy and categorical variables, right? This is just like a linear fit of continuous education years variable. Okay, and now model 3, we are combining both the earnings, we're combining both the education and sex to look at our response variable of earnings. And if I run this regression, okay. So now who can help me out here? Yes.
So even when you control for education and keep it the same, males on average would earn $20,430 more than females.
Yes, that's right. And let's take a look at what this looks like. Yeah.
So, just so I want to try and understand, the intercept is smaller
Mm-hmm.
because you're adding in Why is the intercept? Why is the intercept so high?
We're gonna find out. So let's look at our wages example. So in our first one, we had wages. And let's just say this is education. Our first model was regressing wages on gender, and what we found was males had some number, and females had another number. I can't actually look at what that is. So who can remind me in Model 1 what these numbers are?
It was 24,000, and then male was 46,000.
Yeah, so this is 24K, and then males is 24K plus 22K-ish, something like that. So this is about 46K. So that is what our graph would look like in reference to the results of the first model. Okay. Next, we had wages or earnings on education. And this had something like this. So what is the slope? Can anyone remind me? It's like 4,000
For which one?
for our second model.
4,490.
4,490. Okay. And our intercept,
Negative 21,000, 27,000 something.
negative 21K.
Sorry, 27.
Oh, 27. Okay, great. So those are our two there. And now for the third one, what is happening is this. Actually, let me put this one a little higher. So we've got education, we've got earnings, and actually what we have is two lines exactly, like this. These should be parallel lines, one for male, one for female. The slope for both of these is equal to, what is the number? 4.2K. What is the baseline intercept? Okay, negative 32K. And what is the coefficient for male? Just tell me the coefficient number. 24?
20.4.
Oh, 20.4. Okay, so now what we're seeing are two lines. That education basically is uniformly applied, and so on average, every year of additional education, you're making $4,200 more. Females are on average with 0 years of education, making $32,000, and males are making $20,400 more on average than females. And so at 0 years of education, they would be making about negative $12,000. Okay. Any confusions with this? Is anyone thinking, does anyone have any burning inquiries now that they're saying this? Is there one last thing that we're missing?
All the variables together.
What does that mean? Don't we have all the variables? Oh, but so forget the world of all the other variables. What else can we do here? So, I'm just asking this in a data way, not in a sensitive way about wages. But do we think that men and women that in this data set that the education effect on their earnings is the same?
Maybe there's an interaction term involved.
Yeah, exactly. So I can actually determine whether or not there's a difference. In other words, do I think there should be a difference in the slope? I didn't do anything. Okay. In other words, do I believe that, oh, it's because I'm getting a phone call. Do I actually think that there is a difference in the slopes between these two lines? Okay, and we can investigate that.
Can I ask a question?
Yes, go ahead.
Why for the, so when you run the model, ed plus x, why, how do you, it automatically gives you males?
Yes,
Wha-
because
wha-
females come first in the alphabet.
Okay. How
That's
would
what-
you force it? Do you do?
So you can re-level the factors if you want.
We did with the race.
Yeah.
Oh, okay.
Yeah.
But so you have to factor. I couldn't do it within the model itself and say sex and then select. Or
There's
like-
probably a way to do that, but I don't know how to do that.
Yeah, it's
Yes.
Does this regression method require factors, or can you do it on normal data?
Yeah, so, yeah, that's a really good question. What happens in the regression is that if you feed it like a column of variables that is like categorical in nature, it will turn it into a factor for you. So you don't actually necessarily need to factorize it yourself. The regression will do that. And what I was thinking about was how to describe the fact that that is how it should work, right? Because what does it mean to regress on a character variable? It doesn't really mean anything, right? Like, you can't do letters into like a math equation, right? And so what is actually happening, to explain this really quick, we're doing a quick aside, but I think this is kind of important to know what's happening behind the scenes. So let's say you have, what is happening to my pen? Okay. Let's say you have a table of earnings and then race. And earnings are 10K, 12K, 8K, whatever. And here I have something like white, Asian, black. Let's say I were to do a regression on this where I say LM earnings on race. What's happening behind the scenes is this. It transforms this table So this is what it means to be a factor.
So is this like going from long to byte data?
No. Wait. Kind of, actually.
That's
Yeah.
how I thought about it.
It's yeah, it's not a direct translation in the way that we would think, because you're supposed to preserve some set of values.
Yeah.
But no, okay. I spoke too soon. That's right. This is essentially turning from a long to a wide.
Okay.
Yes. So this would be like this.
And if it was age, would you make it
No,
a factor? Okay.
because age is just a continuous
So
variable.
as long as it's, if it's
Yeah.
numeric, then you can do the regression tool.
Yeah. Speaking about the like long to wide, the reason why I was saying that is traditionally,
You take the values and put them in the.
yeah, there's like a set of values
Yeah.
that would be corresponding to each of these, and then they get populated into
Yeah,
the table.
but here you're just putting dummy binary values.
Yeah, exactly.
Okay.
Which, strictly speaking, I think you're right. I think this is just long to wide. It's just not in the way that I usually think of it.
Okay.
Yeah. But okay, so hopefully, kind of, if you think about this, this is hopefully makes a little bit more sense in the way that we think about generating like beta coefficients, right? Now I have like a table of numbers that I could actually put into a matrix and do calculations. Like I could not do a set of calculations on these words. Okay? All right, so back to this question. If I believe that, they're actually fundamentally different, those slopes, I could actually test that. And the way that you would do that is through an interaction variable. So that is a relationship among three or more variables if the influence is not additive. And so this is this is one of the ways that you can indicate an interaction variable, is just multiplying the variables together. All right. What the heck's going on here? Someone help me out. Yes.
So we're seeing that the interaction term is more significant than the difference caused by just the strict intercept or whatever you want to say.
Okay, hang on. Yeah. So yeah, that's right. But let's just walk through this. What is this intercept telling me?
If you have 0 years of education and you're female,
Yes.
then you're going to make negative 22,000.
Perfect. And then what is this coefficient telling me?
That's each year of education is worth for you $500.
There's one more thing you're missing in this case. And you're female. Yes. So, if you are female, you can ignore these guys down here and just look at here. It is saying you are on average making negative $22,000 when you have no education, and then for every additional year of education, you're making $3,500 more per year. What if you are male? If you are male, then with 0 years of education, you are actually making less than a female. You are making negative $26,000-ish, right? Negative 22 minus 4. And what does this term mean here, this last one? Yeah.
So each year of education is worth $1,800 more than you were female.
Yeah. So on average, a male, each additional year of education, I'm making $5,300 more, as opposed to a female who would only be making $3,500 more. Okay? So this term here, this is our dummy variable, is referring to the difference against the baseline of the female base level, and this one is the slope of education against the baseline female slope of education. And so if we were to go back to our plot, how do I jump back to my, oh, maybe I totally, oh, no, here we go. Sweet. So now I can complete the set of figures here. Oh. I have education, and I have earnings, and now I have 2 lines. I'll have something like this for female. Who can quickly give me the numbers? What are the coefficients for the intercept and the slope?
Minus
Minus
22,000.
$22,000.
Okay. And what's the slope? 35? 3.5, okay. And so our males would have something like this. Male, slope is equal to
1815.
1815, so 1.8k plus 3.5k, and our intercept would be equal to what's the number? Negative minus 4,000, so minus 4k minus 22k, so about negative 26,000. Okay. Does this hopefully make sense to everybody? And now we have our sort of complete set of pictures, right? When we do a simple dummy comparison, when you're just looking at the education, when we expect that there's actually a difference in the earnings for genders, and that there's also an effective education, you get these 2 parallel lines, and then when you interact them, that is basically assuming that there's a difference in the education effect by gender, and thus you have 2 lines with 2 different slopes. Yes?
I can see that the gender coefficient is not statistically significant. So could it mean that chances are that they both start from the same intercept in this combined plot? Like,
Yeah.
well, yeah.
Right here?
Yeah.
Indicating that that's exactly right, that these
Yeah.
would
They
not
be the same.
necessarily statistically different.
So I noticed that when you include the interaction term, the statistical significance of the sex male variable disappears compared to what we saw before. Does that indicate, essentially, how do we interpret that?
Yeah. So basically, Okay.
Yeah.
This is saying on average, men make more than women. And here, this effect is basically saying, when controlling for education, we don't see a difference between the amount of money that a female makes versus a male makes, but we do know that the earnings potential from getting more education is higher for men than for women. Okay. Any questions about that? And this is a great way to use data to highlight discrepancies between populations. Yeah.
I guess this is like a question you can't really easily answer, but it's kind of like, when will you expect interaction terms to matter more? Like, do you base that on just like what the theoretical,
Yeah.
your knowledge about that thing would suggest it might be? Because that like
That's
the easy way to investigate things is just always assume it's a linear effect, and then you just ignore interaction terms, and then for certain things you expect interaction terms, so you add those in.
That is a
You can also add interaction terms for everything, and then
that's a great
it's very
question. And
complex.
yes. And we're gonna talk about this directly pretty soon, but you're kind of hitting the nail on the head here. Yeah, the general advice that you're gonna hear is that you should have some intuitive reason for why you would want to have an interaction term before you introduce it into the model. And so what is the rationale behind that? Okay. What is going on here? Why is my pen so weird? I'll figure this out eventually. All right, x1. How many model configurations are there between my response and my explanatory variable? There's one. It's y on x1. How many combinations are there here? 3. Yes. I should say ignoring the interaction variables. Okay, so this is y on x1, x2, and x1 plus x2. And we can continue on with this x1, x2, x3. So you have x1, comma, x2, comma, x3, comma, x1 plus x2, comma, x2 plus x3, x1 plus x3, and x1 plus x2 plus x3. So that's 3, 6, 7. So we have 1, 3, 7. So hopefully you can see kind of a trend here. The rate at which I can investigate combinations of variables grows exponentially with the number of variables that I add. I think it's 2 to the n. I'll double check that. It's on the order of 2 to the n. Now, what happens if I try to do interactions? How many interaction terms are there between x1, x2, and x3?
If you add in the intercept, I think then it becomes 2 to the n, isn't it?
Yeah, something like that. Yeah.
Yeah.
So, So this would essentially turn into x1, x2, x2, x3, x1, x3 as interaction variables, and x1, x1, x2, x3. And you can actually think of these as just like entirely separate variables, right? This could be z1, z2, z3, z4. So now the rate at which my body of variables grows is growing exponentially. So as I add more terms, trying to investigate interaction terms grows at 2 to the 2 to the n rate. And so there is no possible way, there is no like simplified procedure to try and brute force this in any way. Okay, and so that's why we don't try and investigate all interaction terms in sort of traditional ways. A lot of times the way that this is suggested is if there is like an intuitive reason why we think that something like this makes sense, then we will include the interaction term. Yes?
Is there a difference between, like if, earlier we were talking about doing, like for race, doing the base and the non-base. If you just multiplied all the other ones together, is that doing that, or is that a completely separate thing?
Can you be more specific when you say
Like-
multiply everything together?
Like if you have black as the base,
Okay.
and then you want to see non-black like all together,
Yes.
could you just multiply them all together like that in an interaction term, or is that separate?
You would, so no, you wouldn't do it quite that way. Because technically what you would be doing is so if you had white and everyone else, you couldn't actually sort of multiply these together, because then that would be 0 and that would be 0. So actually the way that you would recategorize this is that you would have a white column and an other column, and then you'd have ones where anytime white isn't 1. And there's like pretty simple ways to do that in R. Yeah. Okay. Great. Any questions about interactions and dummies and categorical variables, all this stuff? Okay, so I've tried to lay out the groundwork for that. It can be still kind of somewhat confusing, and so yeah, don't hesitate to ask questions if you're still kind of working through that. So there's in homework 2, which is posted today, there are a few questions focused on these concepts to make sure that you guys get a solid understanding of this. You know, this type of thing, dealing with categorical variables, dummy variables, interaction variables, this is like a fairly common thing that's going to show up in your regressions and data analysis, so it'll be good to have a firm understanding. Okay. So now, we are going to pivot a little bit. We've kind of wrapped up this section, and we're going to be starting to talk about some concepts that will kind of pervade through the rest of the quarter. So we've highlighted some of the diagnostics, right, of ways that I can tell whether or not a model is good. We've looked at things that commonly people use, standard errors, R squared, right? But we're also trying to identify a holistic set of tools to help us with this diagnostics, right? And so that also includes like residuals and mean squared errors. And I want to back up and think about this a little bit more theoretically. And this is, again, related to this kind of same conversation that we've kind of been having, right? So I've shown this example a few times now where we're talking about, everyone see that? Yeah. Having these data points. And I have some line that goes through all of this. And the idea, right, is we can create a better fit by adding more like curvature to our fits to try and pass through more points, right? And so we've talked about, oh, what if I just do this thing where I go like this, right? And we kind of hinted at this concept of overfitting, right? In other words, well, like, is that line actually really good? Like, what if I had left out some data? What if I had left out some data points that look something like this, right? And these yellow points seem to be reasonably within that sort of bubble of data. But you can see that my distance to the green line is a lot farther from my yellow than the fit to the red lines, right? Like in this particular contrived example that I've made, this green fit, which fits the blue points a lot better than my red fit line, is in fact worse in every single case of the omitted data points. Yeah.
If you were trying to do this sort of, or testing this contrived example out in R, would you randomly tell R write code to leave some data points out and add them in?
Well, we'll talk about that in just a moment. Generate more points, and suddenly model is bad. Okay, so there's like something in between the world of the red line and the world of the green line. And I want to figure out, like, how can I get the best line, right? We're thinking a little bit more abstractly now, right? How can I get the best line to try and fit these things when I run and avoid running into this kind of problem? And so that has to do with an understanding of where an error comes from. So the error refers to the difference between my prediction and where the point actually is. And so this is where we're going to talk about something known as the bias variance trade-off. So I can have a bullseye. It looks something like this. I'm going to draw a couple of these guys. Maybe you've seen these before. So pretend these are like targets on a dartboard. You can have something that looks like this, where I've thrown a bunch of darts and they land right in the middle. Okay, so this is an example of low variance as well as low bias. You could have something that looks more like this. This is where you have high variance, but everything is still centered around on average. And so this would be low bias. I could have a tight clustering, right? So I'm relatively precise, but I would have low accuracy. And so this would be high bias, but low variance. And then I could be right all over the place here. And this would be high bias and high variance. And our error is equal to bias squared plus variance plus noise. I'll write the mathematical equation just for reference, and then we can this is just for a reference point. You don't need to memorize this. So the expectation of the fitted value plus expectation of f hat x minus expectation squared sorry, it should be like so this term is known as bias squared. This term is variance, and this is our noise. And the key thing to note here is when we have overfitting, variance is too high. And if we have underfitting, the bias is too high. And generally what this kind of translates to is this idea where if I have model complexity down here, so what do I mean when I say model complexity? The idea here is in my example where I fit a line through something and then I start getting more squiggly and I pass through more points. And you can imagine as you get more and more squiggly, right, you could just do that thing where I did before, where I have, let's say I have points like this. I could do not complex, somewhat complex, and then super complex model, right? So the idea is as I go from red to blue to green, essentially my model complexity is increasing. And so what does that look like in terms of the error? Well, so actually my bias term decreases as I have more and more model complexity, right? Because I'm doing less and less underfitting, right? I can get closer and closer to my points. However, I have a variance term which will be increasing as a result of, right, or I guess this is leading to overfitting. And what that means is that if the error is the sum of my bias and my variance, then we'll have an error term that looks something like this. So total error. And that is variance plus bias. And the idea is I want to get the lowest total error, okay? And this concept is kind of what we're going to rely on in order to figure out where on the spectrum of red to green I want to be. Okay, that's kind of the theoretical aspect of how most of the models that we're going to talk about basically for the rest of the quarter work. And so keep this in mind as we think about all the sort of model diagnostics into the future. Okay. Let's do questions. Yes.
Will the total error always follow the same shape?
Yeah, in practice, so yes. So this type of relationship is generally pretty much what you'll always find. In practice, like the way the variance relates to the bias may not be as straightforward. Like this might be much higher for a long time, this might be much lower for a long time. You may not see the effect of like variance until like way out here. And it can move around a little bit due to like random variation. We're going to talk about why there's random variation in this bit in a little bit, but generally speaking, the trend should look something like this. But yeah, you might only see like this portion of the curve sometimes, so it can be kind of hard, but yeah, yes.
Does the noise term feature in when you have omitted variables, or how does the noise term feature? Because I see there's a square attached to it, and
No.
how much of a role would that play?
No, omitted variables is bias, right? Think about what that means. It means that you think that there's something related to your outcome that you've left out. And so
Underfitting.
therefore your outcome, you're biasing that output because you've not controlled for a certain variable.
So that'll be underfitting then.
Yes,
Okay.
correct. Noise is just randomness. There's like actual randomness that you cannot control for.
Okay.
Did you have a question?
Yeah, I think you kind of answered, but I'm trying to figure out. So I get why variance is too high, and you fill with it with things that are spread out, and then you just kind of like, connect everything. Like I get with the underfitting, your bias is too high. I don't quite understand why. If the bias is high, because I'm thinking of the dartboard, and if all your stuff's over here, right? Well, is that a bias away from, like, like the high bias, low variance? Like, are we saying like,
Bias means on average your answer is going to be wrong.
yeah, but so you're saying bullseye though is like your line, your fit, right? Or I guess I'm trying to use this visual example to understand, like, because if I have a high bias meaning the majority of like data that you include in your model skews one way, but if it skews one way, then once you fit into that skew, I guess I'm confused how the bias element here, because even if you're dropping variables, like you said, right, you're underfitting because you're creating a line that doesn't actually represent the broader data set. Is that the right way to think about it?
Yeah. So, I believe I know what you were talking about here.
That's good, because I'm like 50% sure.
No, you're putting me on the spot to come up with an example of which I think I can find one. So X and Y. So let's think about this. So there's this one point here that is pulling the line down. When I make a prediction about what the fit should be, and then I compare to my data points, I am systematically underestimating what those values should be. Okay, and actually let me even, can add a couple more points here. Now, let's say that I had a categorical variable that will actually distinguish these two sets of points. And I introduce that into my model. And now I have a dummy variable, which means that I have two lines, right? Like this and like this. I have, in this example, effectively eliminated the underfitting by including another variable, by distinguishing the blues and the greens.
Right.
So that's an example of an underfit that would systematically be biasing the data that you could fix by adding more variables. And in fact, I could, if we think about this particular example, you could go all the way to what's the opposite end of the spectrum where I'm totally overfit. I could add a dummy variable for every point.
Yeah, and
then so what would happen is that I would have a line for every point.
Yeah.
So I would have a whole bunch of straight line intercepts, right, that would pass through every single point. So then that would be overfitting. And so that's what we're talking about here. That's where we are trying to figure out the best place between going from red to yellow and green to like having all the black lines, right? So that would be a simple example of this. And in fact, in this case, this fit with all these black lines, the more complexity that I add to the model, the more I will always improve the quality of the model. Okay? So, yes.
So we go back to the overfitting and underfitting definition.
Yes. Oops.
So theoretically, can we actually say for those model shows overfitting the model generability of model results is relatively low. And for both underfitting, then the accuracy or validity of model results is relatively
Yes,
low.
that's correct. That is exactly right. Yes, that's right.
Thank you. That's all.
I didn't catch what she said.
Huh?
I couldn't hear the thing.
Oh, so one of the ways to interpret this, sorry, can you say that again? It's so the generalizability,
Yep.
generalizability
Yeah.
Words.
of models that are overfit is poor, and then for models that are underfit,
The validity and
the validity of the model is low,
Or accuracy.
or accuracy.
Yeah.
Yes. Yeah, that's another term for these things. We talk about precision and accuracy, like high precision. When these are both high precision, and these two are high accuracy and low accuracy. Yeah. So you can refer to
Yeah.
accuracy as bias and precision as variance. Yeah.
Is the variance in the formula the same variance of the UI or unobservable term that we use to calculate standard error? Or is it, because I'm confused between the terms here.
No. So standard error is like something that's referring specifically to one of the coefficients of the model.
Yeah.
It is referring to how good my estimate is, or how precise my estimate of the coefficient is. This variance is referring to the component of the overall error of the model. So this can encompass, right, if you look here, this is encompassing many variables, right? Because it wraps up all of your x's in the model.
But the f hat x is the fitted value then.
Yes. Yes.
And the expected value of f hat x is the average of the fitted values, the sample average of
Yes.
fitted values.
Correct.
And we're subtracting them. That's not exactly the residual. It's the overall error.
No, definitely. This is not. Yeah, not residuals. Yeah. I can draw that out, but okay, I'm probably gonna get it wrong if I do it off the top. Let me remind me, and I'll draw it for you next time.
Okay.
Yes. Yeah, it's not the residual term. It's a little bit different. Okay, so let's show a example of this. Okay, so this part you guys do not need to follow along, and the code will be posted online later.
We survived the Wi-Fi dropout. We're past the
We're
10
past
minutes.
that,
Sorry.
Oh, cool.
It's fixed.
Yeah, well, I'm recording
The other break it.
through my MacBook Pro instead of through Zoom, but it will be a little bit different. the file size for this, the file size for like a Zoom 2-hour Zoom meeting is like 100 megabytes. And I tested this. The file size of the QuickTime recording is like 30 gigabytes. So
At least we get 4K count.
yes.
4K.
No, it's actually, I think it's actually higher than 4K because I have the like, I'm not going to be uploading a 30 gigabyte video to
I don't think
YouTube.
you're allowed.
Yeah,
to.
YouTube might allow like
Okay. We'll figure out how to do that compression. Well, I will figure out how to do that compression. Okay, I copy and pasted a bunch of code. So again, you don't have to follow along. This is all going to get posted. Let's just walk through this and see what's happening. Okay, we got our classic XY. Hey, all right, great. We've got these data points here. I am actually going to add in exponential explanatory variables. And let's see what happens. So I am essentially asserting that, you know, in that total error chart where I had model complexity, actually the idea is, let's suppose I had like a really big data set. I can just throw in all of the variables, and every variable that I throw in is actually going to increase the R squared of my model, right? Because you're just throwing more data in there, and by sheer randomness, you can do no worse than, you know, not having your variable in. But as you add more and more variables, by sheer chance, you could just decrease the variance of your prediction versus your final outcome, or versus the actual outcome. And so that's kind of what I'm doing here, right? I'm like, okay, I'm going to regress y and x. I'm going to include x squared and x squared and x cubed. And in fact, we should see exactly that happening. So let me jump down here, and we'll just do summary m.1. Okay, my r squared is 0.3879, 0.3879, 0.3893, so we're going up. Great. And 0.3895. What was this? Yeah. And we'll talk about adjusted R squared. So I keep saying we're going to talk about adjusted R squared. We're not there yet, but we will soon talk about adjusted R squared. So don't worry about adjusted R squared for now. And in fact, let's go ahead and run through x1, x squared, x cubed, x fourth, all the way to x to the 50th power. Okay? So this is the code that will help me do that. And then I am going to create the fitted lines for each of these. So that's essentially what's happening here. Don't worry about all the rest of this code. And let's just take a look at this plot. How do you guys remember how I popped this out? Zoom, okay, cool. All right, let me bring this over here. Give it a second to render. Oh man, my laptop is so fast. This used to take like a minute, and I would just, all right, anyways. So what is being shown here? x1, x squared, x cubed. So this model has x plus x squared, x plus x squared plus x cubed. x plus x squared plus x cubed plus x to the fourth, and so on and so forth, okay? And essentially, I'm adding complexity to the model, and the fit of my line starts to get like more and more squiggly, okay? But in fact, it is essentially getting closer to each of my data points, right? And so this is a representation of this concept that we've been doing, where I have the straight line and then I start squiggling it more and trying to get it to pass through as many data points as possible. And somewhere in the field of all of these fits, like one of these is actually going to do the best at fitting against like this random set of data, right? And so you can imagine, let's pull out a couple of data points, train it, and then add those data points back in and see which one does the best. That's kind of the concept that we're working with here. And in fact, we can do exactly that. Let me see, does this include, yeah, we'll see. Oh, it's so fast, I love it. Okay. So in the top left is the mean squared error of my data points that I trained on, okay? So what does that mean? That means I have a line, I have all my points, I take the sum of all of the errors, I square each of those, each of the errors, and then I divide it by the total number, right? And so this top left corner indicates my average error value, okay? And similar to my R squared, the average error is going to decrease always as I increase my model complexity. And that is because it can be, at the very least, the line that gets fitted could be the same as it was before, but now I've added an extra variable, so I have a little bit more flexibility to work with, and so it's going to decrease. And we can see that, right? So 102.24 down all the way to 85.49, and you will not see an instance where this number is larger in the less complex models. However, I have also done a training set versus a testing set where I have taken some points and I have taken those points away from the model's ability to train on them, and then I put them back in, right? So let's say this is, right, our function was like x drawn from a uniform distribution, errors drawn from a normal distribution, y is equal to 1/2 times the x's plus my error. So I did that 100 times, and then let's say I do that for 100 times again, but I leave that out, and then I can put them back in and calculate the error again for those that I left out. So that is called an out-of-sample test, okay? Because the line that I trained on did not include those points. So the out-of-sample test error, that's the bottom right. And in fact, you can see amongst all of these models, where is our lowest out-of-sample error? The first one. And so the first one, if you remember, is the actual model, right? The first one is where we just had y related to x. We didn't have any x square terms or anything like that. And so I can actually say with confidence then, using this technique, that our first model is actually the best model to use, because when we do the out-of-sample testing, the lowest error is the first one. And if you think about this conceptually, it means I can make all of these predictions using any sort of generic model, and the model, the best model that we're going to pick is the model that gives us the best predictions to outcomes that we didn't know the answer to, right? And that's what we want in a model at the end of the day. Okay, so that's kind of an introduction to this technique of finding the lowest point on that total error curve in the bias variance thing. This is how we do it, or this is an example of how we do it, and then I'm going to show next class techniques of actually doing this procedure. Okay? Great. I guess that's it for today. We'll end here, and if you have any questions, let me know. So homework 2 has been posted. It will be due next Wednesday. And the project proposals will be due next Friday as well.